International Conference on Discrete Mathematics. Today's the plenary talk speaker is Professor S. Arumugam from Amrita Viswavidyalayam, Coimbatore, Tamil Nadu, India. Before starting the session, let me introduce the professor, the present day speaker, Professor S. Arumugam. He is a well-known professor almost to all the continents also. And he has started his career in the St. John's College in the year 1968. And he had been there up to 92. And served in different capacities, like at that time, maybe the lecturer and then the reader and then professor. Then he joined in the Tirunelveli Manonmaniam Sundaranar University in the year 1992 as professor. And then he continued his service till 2003 in the same university in different capacities in the administration as well as the academic. And after that, he joined as a senior professor in the Kalasalingam University. Then there also he has served in many capacities as Dean R&D and a senior professor in research in different capacities. And after that, he had been the conjoined professor, adjunct professor, visiting professor, adjunct professor in different countries, in fact, in Australia, in USA, in UK, and in our country, in India, also in different institutions like BITS Pilani and Amrita Viswavidyalayam, Coimbatore, etc. This area of specialization is many. Graph theory is one of the subject, and he is also well versed, and he has done many work in the fuzzy logic and its applications, pattern recognition, and topology, geometry, and cryptography, etc. To his credit, he has delivered so many lectures, in fact, roughly more than 350 lectures delivered during his tenure, and he is motivated many of the young researchers to do research in graph theory, and too in many popular areas like labeling and domination, etc. And then he has organized 29 the programs like seminars, workshops, conferences like this. And then he has published more than 260 publications in the internationally reputed journals. He has also published 20 books, which the books authored by Professor Arumugam is very popular in the Tamil Nadu for the undergraduate as well as the postgraduate students. He has written the books in a simple language to understand even the normal students also. He has edited more than 15 books, proceedings of the conferences. Altogether, he has guided more than 50 students as a guide as well as a go-guide, and he has also visited many countries in a different visiting program. And almost all and above that, he had been a director for the NCOD Math sanctioned by the Department of Science and Technology. That means the National Center for Advanced Research in Discrete Mathematics. So he is a well-known professor in discrete mathematics, and he is known to almost all the youngsters, in fact, who are been working in graph theory as the research area. So the conference organizers are very proud to have such a nice person in the conference as one of the plenary speaker. And today, and his the title of the talk is Certified Domination in Graphs. So with these a few words as introduction, I invite Professor Arumugam to deliver his plenary talk in the title Certified Domination in Graphs, and the time is 10 to 11. So I think a professor will also stick on to the time.
Yeah.
Thank you, sir.
Thank you very much for your kind words. I'm happy to be a part of ICDM, organized by my own department at MS University, jointly with ADMA. And the topic that I'm going to talk today is very, very relevant in the pandemic situation of today. This is based on a paper published in our AKC journal last year, 2020, by Tetlov, Lemarsica, Top, Zierman, and Zielinski. The title of the paper is Certified Domination. What is the motivation for the concept given by the authors? That was very interesting. That's why I took up this topic, and I have written 2 more papers on this now. So you have exactly 3 published papers on this concept. And we are working on the 4th paper, and it will come out within a week or 2. So why the concept is interesting? See, in this pandemic situation, people need to be provided with service. So some officials are serving the civil. Okay. So in hospitals, patients are given service and so on. So providing service mechanism. That is they have modeled using the concept of certified domination. So the situation is you have a set of officials and set of civils. For any civil, there is an official who can serve him. Okay. For any S in W, there is an official in D who can serve the member W, member in W. And he demands that whenever an official is serving X, there's another civil Y which is adjacent to V and observes V. In other words, there's another civil is acting as a witness to see to it that the official do not abuse V. So he demands that whenever an official serves a civil, another civil is adjacent to the official and is watching him so that the service mechanism is monitored. Okay. So what is the minimum number of officials to guarantee such a service mechanism in a social network? So this is the problem. Okay. So minimum number of officials to guarantee a service mechanism satisfying the 2 conditions. Okay, fine. So motivated by this observation, they introduced the concept called certified domination in graph. The social network is considered as a graph where we have a set of officials and set of civils. Okay. So a dominating set D is called a certified dominating set. If for any vertex in the dominating set, number of neighbors of B outside D is either 0 or at least 2. Okay, it's either 0 or at least 2. 0 means all its neighbors are within D. Okay, he doesn't serve anybody. Okay, he is perhaps an official who is monitoring the whole mechanism. So NV intersection B minus D is 0 means all the neighbors of B are within D itself. Okay, that official never serves anybody. It cannot be 1 because he wants a condition that whenever an official serves a civil, another civil should be adjacent to him to prevent abuse. So he should not have exactly 1 neighbor. So whenever a vertex dominates something outside, it will dominate at least 2 members. Such a dominating set he called certified dominating set. And the minimum cardinality of a certified dominating set is denoted by symbol gamma CER. So this is the concept developed and presented in the first paper published in 2020. I'll give a quick summary of some of the known results presented by the authors. Okay. First of all, let me take this example. Here is a tree where I have labeled 7 vertices. Those 7 vertices forms a certified dominating set for this tree. Because you see, V1 has 2 neighbors outside, V2 has 2 neighbors outside, and so on. And V5 has 4 neighbors outside. V7 and V6 have 0 neighbors outside D. Okay, so this is a certified dominating set for the tree. It's a minimum cardinality certified dominating set. Because there are 4 leaves, I can't omit any of this V1, V2, V3, V4. And then V6, V7, if I omit any of them, the certified domination condition gets violated. Suppose you omit V7, it is still a dominating set, but not certified dominating set, because then V6 will have exactly 1 neighbor outside. So I cannot omit V6 or V7. So this is a minimum certified dominating set for the tree. So for this tree, gamma CR is 7 and gamma is 6. Okay, gamma is 6 and gamma CR is 7. This is a very simple example to illustrate the concept of what certified domination is. Okay. So for the tree, it is 7. For path, for n greater than or equal to 5, it is simply the domination number, no problem. And only when n equal to 2 and 4, you see you have to take all the vertices. So when n equal to 2 or n equal to 4, all the vertices have to be taken. Why? When you take n equal to 2, it is K2. If you take one vertex, it is exactly 1 neighbor outside, which is prohibited. So you take both of them. Similarly, for P4, the support vertices you have to take, or the leaf you have to take. Once you take one of them, you have to include the other, because only 1 neighbor outside is not permitted. So you see that there are several graphs for which gamma CR is the whole of n. For P4, it is all the 4 vertices you have to take. There are several, actually there are infinite family of graphs for which gamma CR equal to n. It behaves completely in a different way than the usual dominating set and domination number. Okay, for the cycle, it is again the domination number. The complete graph, except for K2, it is domination number. And for the complete bipartite graph also, it is just a domination number. Okay, so these are some simple examples of certified domination number of some of the standard graphs. Okay. So the first observation is that every support vertex of G must be in every certified dominating set. What's a support vertex? A support vertex is one which is adjacent to a pendant vertex. Okay. It supports the pendant vertex. It's called a weak support vertex if there's exactly 1 pendant neighbor, and strong support vertex if there are at least 2 pendant neighbors. Okay. So a support vertex has a pendant neighbor. So a support vertex must lie in every certified dominating set. It's an obvious observation. Because for domination, you have to put either the pendant or the support. If you put the support, then you see why the pendant also should come inside. The pendant has exactly 1 neighbor outside, which is not permitted. So once you put a support, pendant must automatically enter. Conversely, if you put the pendant, the support will enter. So every support vertex is in every certified dominating set. So this gives you an infinite family of graphs with gamma CR equal to mod Vg. Simply take any graph and put pendant at every vertex. Take H corona K1. That's any graph, attach a pendant at every vertex. Then by this, all the support vertices you have to put in. Once you put the support, automatically pendants enter, and therefore you see gamma CR equal to n. So we have infinitely many family of graphs for which the certified domination number is n, the total number of vertices. So this theorem actually says that for a connected graph, gamma CR is mod Vg if and only if it is corona of H corona K1. Otherwise, only isolated vertices can enter. So gamma CR is number of vertices if and only if it is either Kn bar or the corona or union of these two. So for connected graph, gamma CR is N if and only if G is H corona K1. Okay. So this behaves in a completely different way than the usual domination number. Okay. So the fundamental question is for which graphs gamma CR and gamma are equal. As you see, we have a large collection of graphs for which they are equal. See, all complete graph with n greater than or equal to 3, all complete bipartite graphs except K2, okay, all cycles, all paths with more than 5 vertices, all have the property that gamma C are equal to gamma. Okay. So complete characterization is an interesting problem. Though in the base paper, the authors have given a theorem, gamma C are equal to gamma if and only if something is satisfied. But it doesn't give any characterization. It only says gamma C are equal to gamma if and only if there exists a gamma set D such that for every weak support vertex, the non-leaf neighbors are not contained in D. It doesn't say anything about the graph. It says a dominating set of a particular type must exist. But that particular type automatically turns to be a certified dominating set. So those authors who put it as gamma CR equal to gamma if and only if there exists a gamma set D such that something is satisfied. That something is satisfied simply says it is certified dominating set. It's actually not a characterization theorem. But they have a theorem that a gamma set is a certified dominating set if and only if something happens. Okay. So characterization of graphs with gamma CR equal to gamma seems to be a first interesting unsolved problem. Okay. Very nice question to work at. Fine. Then we shall. This is the more or less the content of the first paper, the base paper. I collaborated with 2 of my colleagues at NIT Warangal, where we took up the study of algorithmic aspects of certified domination. So title of the paper is Algorithmic Aspects of Certified Domination. It has also been published in the journal Communications in Combinatorics and Optimization. That's the title of the journal, where you can see the paper online. You can download the paper online. The base paper also you can download from our journal website. So let me again show that paper. So this paper is downloadable from the AKC journal website. This is a base paper on certified domination. The second paper, Algorithmic Aspects of Certified Domination, is also freely downloadable from the journal Communications in Combinatorics and Optimization. Okay. So let me briefly look at the algorithmic aspects. Okay. Okay, second. Okay. Okay. So we first prove that the certified domination problem remains NP complete for split graph, star convex bipartite graph, and cone convex bipartite graph. What is star convex and cone convex bipartite graph? We shall see. Okay. Let me put the definitions somewhere. Let me see where I have the definition. That definition is missing. Doesn't matter. I'll explain the definition. So you take a bipartite graph with bipartition V1 and V2. Okay. You take a bipartite graph with bipartition V1 and V2. I am going to associate a tree with a bipartite graph. Here another tree, completely new tree. You associate a tree T with a bipartite graph whose vertex set is one of the parted sets, say V1. So the vertex set of the tree is the partition set V1. A new tree is associated with a bipartite graph. It has the property that if you take any vertex in V2, take all its neighbors in V1, and take the subgraph induced by V1 in the tree T, because the tree T has V1 as the vertex set. Okay, the tree T has V1 as the vertex set. For every vertex in V2, look at its neighbors in V1 and look at the subgraph induced by that neighbors in the tree. If that is a subtree, then the bipartite graph is called a tree convex bipartite graph. Okay, so a tree convex bipartite graph is a bipartite graph with an additional requirement that there's a tree associated with the bipartite graph whose vertex set is one of the partite sets, and with the property that for every vertex in the other partite set, its neighbors induces a subtree of the tree. In such a case, the bipartite graph is called a tree convex bipartite graph. It's a subclass of bipartite graphs. Okay. And in algorithmic study, the people look at such subclasses and try to see whether the problem is linear time solvable or remains NP-complete in such subclasses. Okay. So it's a tree convex bipartite graph. If the tree that you associated is a star, then I call it star convex bipartite graph. For example, the complete bipartite graph is star convex. If the tree that you associate is a comb means path corona K1. It looks like a comb, okay? Path corona K1. Then it is called comb convex bipartite graph. Okay. So we are going to prove that CFDP, that is certified domination number problem, remains NP complete for comb convex bipartite graph as well as star convex bipartite graph and split graphs. And we are going to reduce the problem to the well-known NP complete problem called exact cover by 3 sets. What's an exact cover by 3 sets? We are given a set with 3 Q elements and a collection of 3 element subsets of X. Okay? We are given a set with 3 Q elements and a collection of 3 element subsets of X. Okay. I want to find a collection of a subcollection of C with exactly Q sets which covers the whole of X. Because you see that each element of C covers exactly 3 elements of X. Each element of C covers 3 elements of X. It's a 3 element subset. So from that collection C, I want to extract Q disjoint subsets whose union is X. Thus there exists a subcollection C dash such that every element of X occurs in exactly one member of C. That is, the C dash subsets of X forms a partition of X. It partitions X into Q disjoint 3 element subsets. Such a subset C dash is called the exact cover. Okay. So given a collection C, does it contain an exact cover? This is called the exact cover by 3 sets, X3C. This problem is well-known NP complete problem. Okay. It's a well-known NP complete problem. We are going to use this problem to prove that the certified domination problem remains NP complete for some classes of graphs. The advantage is given an instance of X3C, an instance means a set X with 3 Q elements given and a collection of 3 element subsets is given. This is an instance of the exact 3 cover set problem. And the solution is a subset C dash of Q elements which exactly covers X. So given such an instance of the exact 3 cover problem, I construct the graph. the incidence graph. Namely, you take the bipartite graph with vertex at x and c. One partite set is x, other partite set is c. Okay. X equal to x1, x2, xq, c equal to c1, c2, cq, cm. Okay. Then I join any vertex of C with three elements in which it contains. The C is a three-element subset of X. So join an element of C to three elements to which it belongs to. So in this case, I get a bipartite graph. This I call incidence graph of this instance of the X3C problem. So incidence graph is a bipartite graph with vertex at X union C, and an element of C is joined to exactly three elements of X to which it contains. Okay, an element of C is joined to exactly three vertices of X which it contains. So this is called the incidence graph of this instance of X3C. Okay, so given an instance of X3C, I take the graph H with vertex at X union C, and Xi is adjacent to Cj if and only if Xi belongs to Cj. So this is called the incidence graph of the given instance of the exact three cover problem. Okay. Now I simply make this portion complete. I make the portion C complete. Then it becomes a graph where one side is complete, other side is independent. You know, this is what is called a split graph. So I make this side C complete, and that's X as independent. So from the instance of X3C, I get a split graph. Okay. Then I prove that the instance of X3C as an S answer are equivalently, there are Q subsets which covers the set X exactly if and only if those Q subsets forms a certified dominating set of my split graph. So this is the outline of the proof. Okay. So given the instance of X3C, I construct a split graph by taking the incidence graph and making the portion C as a clique. So this gives me a split graph, and then it is proved that X3C problem has a solution C dash if and only if the corresponding subset C dash in the graph forms a certified dominating set. So this proves that the certified dominating set problem is NP complete when restricted to split graphs. Okay, fine. So this is outline of the proof. It's what I already explained. Okay. Now, if you want to make it for convex bipartite graphs, instead of making this complete, I'll put some more small adjustments so that it becomes a convex bipartite graph, tri-convex or star convex bipartite graph. Okay, I take the incidence graph. It's already a bipartite graph. I add little more vertices and to make it a tri-convex bipartite graph, and then again prove that the X3C has a solution if and only if that tri-convex bipartite graph has a certified dominating set, and thereby proving that those problems also remain NP complete. Okay. The idea is very similar to this. What I'm going to is, if you want a star convex bipartite graph, I do the same thing, that take the incidence graph, add a new vertex to X and a new vertex to C, and then you make a star X union as vertex set and A as the central vertex, and do the same thing. So the construction is slightly adjusted. I take the incidence graph. Always I'm dealing with the incidence graph. Okay. I take the incidence graph, make some modifications in the construction in such a way that when the exact three-cover problem has a solution, that solution itself serves as a certified dominating set in the graph that I have constructed. That's all. Okay. So I take the incidence graph and add two more new vertices and make one X union as a star. It continues to be a bipartite graph. And this graph has a certified, this graph is star convex because the subgraph induced by the any neighbors becomes a subtree of that tree that I have associated. And this graph has a certified dominating set if and only if the X3C has a exact three cover C dash. So C dash becomes a solution of, if C dash is solution of the exact three cover problem, C dash union A becomes a solution of the certified dominating set problem and vice versa. Okay. And similarly for comb convex, I am again making only adjustments. Namely, I will take the instance graph, add an edge, and then create a comb somewhere around that. So the type of the proof is very similar. Starting from the incidence graph of the instance of X3C, make some adjustments in the construction of the graph and see to it that the solution of the three cover problem, exact three cover problem, with one or two more vertices becomes the solution for the certified domination problem. Thus proving that the certified domination number problem is NP complete for most of the even subfamilies of bipartite graphs. Okay. And we also developed an algorithm to construct a certified dominating set starting from a dominating set. Starting from any dominating set, whenever there's a vertex with exactly one neighbor outside, I add that neighbor or add some other neighbor of that so that condition is blocked. Then I end with a dominating set, which is a certified dominating set. And we have checked that for in some rare cases, it deals to a dominating set, which is also certified dominating set. Okay. So we have got a simple algorithm to construct a certified dominating set starting from any dominating set of a given graph G. And in some cases, we verified that it turns out to be a gamma CR set. So which graphs admit a gamma set D such that the above algorithm gives a gamma CR set. Because you got some examples of such graphs. Okay, which graphs admit a gamma set D such that if you apply this algorithm and construct a certified dominating set, that automatically becomes a minimum certified dominating set. Okay, we have got some examples of this type. That's why we have posted as a problem in our second paper. So for which graphs I can construct the gamma CR set from a gamma set? That is the basic question. For which graphs I can construct a gamma CR set from a gamma set? For example, let me go back to the corona example. Okay, this corona example, here H is a dominating gamma set. So you've taken a graph H, put a pendant everywhere. Okay, you got a dominating set for G, means it is the whole of B of H. Or you have to put a pendant. So here DH is a minimum dominating set of G. It's a gamma set of G. DH is a gamma set of G. Everything outside is a pendant. So to make it certified, I have to put all of them. So my algorithm will give that set. So for this graph, if you start with a gamma set and apply my algorithm, it gives a gamma CR set. Okay. So there are several classes of graphs for which applying this algorithm starting from a gamma set gives a gamma CR set. For which graph it exactly does it is a very interesting unsolved problem. It may not be difficult, but it's not so easy also. We are trying at it. We are trying at it. It's nice question to look at. Okay. So this is the roughly the content of the second paper on certified domination. Then we have now got a third paper which is already gone to the review process. I'll tell a small positive story at this point, how the third paper got into motion. I gave a lecture at Ramanujan College, Delhi in a faculty development program. Around 200 participants were there, where I talked about two major topics, graph labeling and domination, and I connected them by one theorem, because I have proved one theorem where a graph labeling parameter is obtained as a domination parameter. A graph labeling parameter is equal to a fractional domination parameter. So I was connecting domination and labeling, and I posed several problems for the researchers in that conference, where I also mentioned about this certified domination set and some of the problems here. At the end of the talk, I post an invitation that anyone who wants to work on this topic can approach me, but with one condition, that that person must be a research scholar, full-time research scholar who has already completed coursework. And he must approach me along with a guide. I put these conditions and said any such person can approach me to collaborate with me on any of the topic. Okay. This is what I proposed in that conference organized by Ramanujan College, Delhi. The next day, I got a mail from one research scholar from University of Mysore and said he's interested in working on certified domination. But he said, I am not satisfying one of the conditions you have put. Namely, I have not completed the coursework. Will you accept me to collaborate? But it's not my fault. Because of the pandemic situation, my coursework examination is being postponed. But I have already published one paper. So I would prefer to come and work with you on certified domination. His guide also is interested. So I said, let us work together. So this collaboration emerged from a workshop, a faculty development program organized at Ramanujan College. And we wrote our first paper. We called it, the title of the paper is A Domination Model for an Efficient Service Mechanism. That's how I titled the paper. A Domination Model for an Efficient Service Mechanism. It's already in the review process. And in the acknowledgement part of the paper, we have clearly stated that this collaboration emerged from the FDP organized by Ramanujan College, and we thank the principal and the convener of the college for having provided the platform for this collaboration. So with this acknowledgement, we have submitted the paper to a journal. It's just a story to motivate young researchers that such conferences should be a good platform for you to expand your network. Okay. So let me go to the third topic, third paper on certified domination, which I call full degree certified domination. See, whenever we have a service providing mechanism, it will be nice if there is one official who is adjacent to all the remaining officials. He's a leader who monitors the entire service mechanism. Okay, if there's a man who controls the entire service mechanism, it's good. It will be more efficient. Okay, So motivated by this observation, I coined a term called full degree certified domination. Not all graphs may have such a certified domination, but it was not a problem. So I take a connected graph and I take a certified dominating set. If there's a vertex V in the dominating set such that V is adjacent to all the remaining vertices in the dominating set, then such a dominating set I call full degree certified dominating set or FDC set. Full degree certified dominating set, and the minimum cardinality of a full degree certified dominating set I call gamma suffix CER superfix FD. Full degree certified dominating set. And a graph which admits such a FDC is called FDC graph. Because not all graphs admit a full degree certified dominating set. We'll show it to you quickly. Okay. Not all graphs admit a full degree certified dominating set. Because you can easily see that. Suppose you take a graph with a full degree certified dominating set. So your dominating set, one vertex is adjacent to every vertex in the dominating set. So all the vertices within the dominating set are at distance less than or equal to 2. Take a vertex outside the dominating, take two vertices outside the dominating set. If one of them is adjacent to a vertex in the dominating set, then you see the distance becomes at the most 3 to all the dominating sets because that's already a star. If both of them have a common neighbor in D, no problem. Its distance is 2. If both of them have different neighbors, because of the certified domination, another neighbor will be there and the distance will be at most 4. So if a graph admits a certified full degree certified dominating set, the diameter is less than or equal to 4. It becomes a very small class of graphs. So from an application perspective, it is not very efficient. That's why we may say that. So to justify that, we have put that though any graph the diameter greater than or equal to 5 is not an FDC, it is not become an issue in the application perspective. Because you take any graph, take a certified dominating set, add a new vertex and join it to all the vertices in D. That's all. Add one more vertex, I can make it an FDC graph. So from the application perspective, this restriction is not very disadvantage. Okay, we can easily overcome the disadvantage by just adding a new vertex. That is, appoint an official who is a leader for the service mechanism. That's all. So from the application perspective, this restriction that an FDC graph has diameter less than or equal to 4 is not a big disadvantage. Okay, it's not an issue from the application perspective. So we justified the concept by putting this observation in the paper, and the paper is almost getting through. Okay. Let me give a quick summary of some of the results we have got. First, if you have a graph of order n, the certified full degree certified domination number is 1 if and only if the maximum degree is n minus 1, the n is at least 3. And it is 2 if and only if there's a connected dominating set such that both the vertices in the dominating set have degree at least 3. It's if and only if. Say, certified domination number is 2 if and only if there is a connected dominating set D such that both the vertices in the dominating set have degree at least 3. So simple observations. We have completely characterized which trees are full degree certified dominating trees. We completely characterize the graphs. We construct a family of trees. Okay, we construct a family of trees. Okay, by something starting from a star, you construct a family of trees, and we proved that a tree is a certified dominating full degree certified dominating FDC tree if and only if it's a member of F. Okay, so you have explicitly constructed all FDC trees and proved that a tree is FDC tree if and only if it is a member of a family F. What is the family F? Start from a star at any pendant vertex. Attach at least 2 pendant vertices or no pendant vertex. That's all. At every pendant vertex, attach at least 2 pendant vertices or no pendant vertex at all. And this is a family of trees. And we have proved that a tree is a FDC tree if and only if it's a member of F. In a similar way, we finished more or less unicyclic graphs. So for an FDC graph, we have got a complete characterization. So for a FDC tree, we also got the number exactly. It is either 1 or 2 or 3. For a FDC tree, the certified domination number is either 1 or 2 or 3. It comes directly from the if and only if theorem and the characterization. Okay. So quickly, you got an upper bound. Okay. So this is about full degree certified domination in graphs. Now we are looking at the 4th paper on total certified domination, which seems to be more realistic than the full degree, because for a total certified domination, if you have a dominating set which is certified, whenever a word is an official source of the civil, another civil is standing as a witness, another official is standing as a monitor. So for a total certified domination, the service mechanism is monitored by an official and witnessed by a civil. So that is also interesting, but we found very surprising results in total certified domination. In fact, we are able to construct infinite family of graphs for which the total certified domination number equal to n. And we are finding it very difficult to find a characterization of all graphs for which total certified domination number is n. But the work is in progress, and we hope that within a period of 15 days, we shall be able to communicate our 4th paper on certified domination to a nice journal. And there are so many other things which can look at. Even for standard graphs, computing gamma CR is families of graphs. It's going to be very interesting and difficult. Even for hypercube, it seems to be very difficult. Finding exact values of the certified domination number, or even several classes of graphs, doesn't look very easy. Okay, so the problem is very interesting, application oriented, and lot of scope for further work. So we have only 2 published papers on the concept, 1 under review, and 4th on the verge of communication. Otherwise, the whole topic is open for further investigation. So you're most welcome to work further on certified domination and its variations. We can introduce your own variations of certified domination. See, there are so many models of domination. Try to create your own model of certified domination and see whether it is worth studying. Okay, it's interesting. So with this, I'll wait for questions and discussions on the topic.
Thank you, sir. Thank you so much for your very nice lecture on certified domination and its variation of parameters. So now it is time to ask some clarification questions by the audience. Please.
Sir, one question. When the diameter is getting reduced, the problem gets more complicated. Do you feel? That's what you mean to say when diameter is less than or equal to 4?
Not complicated. From the application perspective, people may say not applicable for all graphs. It's only for a very small graph you are doing it.
Oh, okay, okay.
The problem is still remain complicated.
But mathematically, how the problem seems to be when the diameter is getting reduced, or it is less than or equal to 2, because we come across
to do even for diameter 2, it is not easy.
it is not easy. That's what
It's not easy.
So it is a
Computer.
mathematically worthwhile problem.
Mathematically, it's a very interesting problem.
Yeah,
it's a very
that's what I
interesting
want.
problem.
Yeah.
Yes.
Because we come across several classes of graphs in which diameter is 2, 3, and we have got plenty of classes with other properties.
Correct.
So can we get into that? That's what my concern.
Correct.
Okay, so thank you.
Still is completely unstudied. Yes.
It's yeah.
Right.
Is there anything of regularity or any, even in the case of I for cube, you say that the problem is complicated or tougher. So the regularity or anything of that nature doesn't help much.
Regularity doesn't play any role.
Any role.
Okay. What I am trying is start from a gamma set and try to construct efficient certified dominating set. That will be the most useful approach for application.
So the tools of domination can help some or other way.
What we are like that we developed only algorithm, but sometimes it is very large set.
Yeah.
That's the only problem.
Okay. Thank you, sir.
Yeah.
Any other questions?
There is a question in the chat box. Can I read, Professor Muthuswamy? Or
yes,
shall
sir.
you read?
Yes.
You please read.
Yes, sir. You please.
Okay,
you
I
please
will read.
Okay.
Sir, is it allowed that if an official is serving in civil A and B is witness, and while serving civil B, then civil A is witness?
Okay. I don't know. That is simultaneously, just two officials are serving and they are complementing each other as witnesses.
Yeah.
The problem doesn't prevent it.
Okay.
It doesn't prevent this.
Somebody put it in the chat.
This.
I think
the vertex in the dominating set must have either two neighbors or no neighbor outside.
Okay.
That's the only condition you have put. Okay. It should not have exactly one neighbor outside. That's all. So that condition is still satisfied. So this situation is permitted, definitely. Theoretically, it is permitted.
Okay.
Only when you look at it now, from the application, it looks hard.
Yeah.
That's why he is putting the question. That's good.
Okay. Anybody else?
Any other question in the chat box?
No, Professor Muthuswamy.
Okay. If there is no questions, shall I have a clarification? There are so many parameters existing in the domination.
Right.
And this is a new parameter introduced, and very few papers have been published. And it's good to research work for the youngsters or the freshers. Is there any relation already identified between these existing parameters and the new one?
No. It is just 3 papers have come so far. One is a base paper.
Okay.
Another one is my paper on algorithms. Third one is full degree certified domination. So which is connected to other domination parameters itself is interesting.
Yes. And that too, you have already quoted that the problem is NP complete.
Yeah.
The problem seems finding the parameter itself, it seems to be NP complete for the general family of graphs.
Even from small family of bipartite graphs, it is NP complete.
Yes.
Yeah.
So that shows the difficulty of the system.
The problem is interesting, and we can try for which graphs we can find the polynomial time algorithm to complete the parameter.
Okay.
That will be very interesting. Computer scientists can try this because it is a really applicable model.
Yeah.
That way, one can try to find classes of graphs where the parameter can be computed in polynomial time.
And nowadays, the interdisciplinary research is coming up. So this is one such provision. This problem gives us such a provision to interdisciplinary to the other subjects also. Okay. Okay, if there is no other questions, we thank Professor Arumugam for a nice and illustrative lecture on the certified domination. The new area the youngsters can pick up quickly. They can publish quality papers in the internationally reputed journals, and he has also discussed the various parameters of this certified domination, and the difficulty level of the problem, and the motivation behind the study, the application side, everything. So on behalf of the organizing committee of ICDM21, I thank Professor Arumugam for his wonderful lecture in this August audience. So I thank once again for the opportunity given to me to share this session